All right, welcome again to the Real-Time Digital Signal Processing Lab course at the University of Texas at Austin. We're on Lecture 6, Part 3, so we're on infinite impulse response filters. And I'll make one comment from last time. So we talked about notch filters last time. I'll go back to that slide just for a reference. So this was an example of a notch filter. This was from Part 2, sorry, it's from Lecture 6, Part 2. So the notch filter is here on the far right. And in the notch filter case, we put the pole and zero locations at the angle corresponding to the frequency that we want to, oh, so that's the all pass, sorry. Wrong filter. So in the notch filter, we put the zero and the pole at the same angle, which is the frequency we want to eliminate, and the zero goes on the unit circle, and the pole is just back from the unit circle. And this gives us a really good, almost an all-pass response, except that the frequency we want to eliminate, which is zero in the magnitude response, and it'll be a little bit of a stop band and transition band around this frequency value. One of the applications of the notch I mentioned last time, which is to remove a power line frequency that may be interfering with us at 50 hertz if you're in Europe or 60 hertz here in the United States. Turns out there's another interesting application, which is in treating ringing of the ears, which is tinnitus. So in this damage to the ear, there's a tone that rings in your ear at a certain frequency, and that can be measured by a specialist in the field. One of the treatments for that is to take all the recorded music that the person with this condition would listen to and pass it through a notch filter to remove the frequency at which the ears ring. Because if that frequency is present in the audio they're listening to, it causes a resonant response. So it grows really strong almost without bound. It's quite painful when that frequency is present with any strength. So you can just pass all the audio that they want to listen to, all the recorded music, through a notch filter and get rid of that particular frequency to make it more easy to listen to that music. It's an application. All right, so we've talked about so far in Lecture 6, we've talked about, we've had 2 parts so far. We talked about the role of filters. We talked about filter structures, biquad, direct form, and we looked at the impact of poles and zeros on frequency response. Now we're going to talk about stability, ZLaplace transforms, and I want to start, I guess, before we get into stability, I want to go into, which will be slide 13, so we'll start there. Oh, sorry, slide 14. So we'll start with stability. And we've talked about bibo stability already, and here's just and I'll give you a derivation for this condition in just a second. So for an infinite impulse response filter, this is a big question. Is it bounded input, bounded output stable? And again, if it isn't, there are some applications for filters that are not bounded input, bounded output stable. Can you give me one such example, one application? So it won't be a filter anymore. It'll be if it's not bibo stable, it won't be a filter. So can you give me a use of a bounded input, bounded output, unstable LTI system?
Like an oscillator?
An integrator is an example, and an oscillator is an example. So both are useful. The discrete time integrators are running sum over time. And it's okay. It's still useful, even though it's bibo unstable. An oscillator is useful, even though it's bibo unstable. So again, but for a filter, we want our filters to be bibo stable. All right. So how do you define this mathematically? Well, bibo stable means that if for any input signal, so a discrete time LTI system is bounded input, bounded output stable. If for any bounded input x of n, and by bounded, we mean that the amplitude is bounded by a finite number in absolute value. So the absolute value of the input x of n is always less than or equal to an absolute value, some finite constant, capital B1. Then the filter response, y of n, is also bounded And this has to hold for all bounded input signals, right? So for all possible bounded input signals, I always have a bounded output signal. Right. Now it turns out this is nice because this actually comes out of the convolution property for discrete time LTI systems. Now I'll have a derivation in just a second for that. Here's the proposition, which I'll derive in just a second using the overhead document camera. Proposition is a discrete time filter, or more specifically, an LTI system, with an impulse response of h of n is bibostable if and only if the impulse response in absolute value sums to a finite number. And that does come from the convolution. I'll show that. And a couple of interesting observations from this is that every FIR, every finite impulse response LTI system, even after implementation, is bibostable. And the reason for that is that if I look at what happens for the FIR case, my summation, this becomes, for the FIR case, this becomes a finite sum over the length of the impulse response. So I'm summing up a finite number of finite values. Our impulse responses don't have amplitudes that are infinity or minus infinity. So our FIR filter has finite values for the coefficients for the impulse response amplitudes. So I'm taking a finite number of finite values. I have to have a finite result. Okay, so FIR filters, even when implemented in fixed precision, floating point, whatever it is always bibostable. Always. That's a big advantage for FIR filters. If you look at this formula, you'll see that for the other case, which is the infinite impulse response case, I want my impulse response h of n to die out fast enough so that if I sum over all n, then I get a finite answer. This will happen. This will correspond to modes in the impulse response that are exponentially decaying with time, with discrete time index n. This corresponds to poles that lie in the unit circle. Okay? And so why is that? So if I think about, there are only 3 transform pairs to really use in a class on a regular basis. The rest we look up. One of those transform pairs is a exponential sequence. And what is the Z transform for that? One over 1 minus a Z inverse. Very good. Z to the minus 1. And what's the region of convergence for this? You can pass it off to a friend. I hear. Well, not Z. It's going to be not Z, but magnitude of Z. Good. For absolute value of Z, what? Greater than magnitude of A. There you go. So what does this mean? So if my pole is inside the unit circle, the pole location is A, right? A is just the root of the denominator. So the pole location is at A. This corresponds to a mode in the impulse response. It's A to the n step n. This A to the n step n will decay with increasing little n, provided the absolute value of A is less than 1, which means that the pole is inside the unit circle. So that's condition 2. Okay. So that's where it comes from. So eventually we pretty quickly lose sight of this, of where this comes from, but I wanted to point out where it comes from, and now I want to derive this particular result, this proposition. Okay, again, we have an LTI system. The impulse response is h of n. The input is x of n. And the output y is simply the convolution of the input x of n and the impulse response h. We can write this as a convolution because it's what it is. So if we write out the convolution definition, it's going to be the sum of little m from minus infinity to infinity of the impulse response h of m. We'll hold that in place, and we flip and slide x about h. So this is x of n minus m. So again, m is this placeholder of convolution. Little n is the outer discrete time variable. Okay. So if I take this now, and what I want to know is this bounded for a bounded input? So I want to know what's the absolute value of y look like. So the absolute value of y, we simply take the absolute value of both sides, which is fine. And now we can start getting closer to an answer. So here's the absolute value of both sides. Now, because it's an absolute value, I can say that this absolute value of sums is less than or equal to the sums of the absolute values. Furthermore, a product of two absolute values is just the product. So the absolute value of a product is the product of the absolute values. We've seen this many times. So now I'm getting closer to the answer. For the case of bounded input, bounded output stability, the input signal is considered to be bounded in amplitude. So it, as I had on the slide, the magnitude of x is less than or equal to this capital B1, which is finite in value. So again, I can take this result here and make it less than or equal to so if I replace x of this absolute value of x of n minus m by the maximum value it could possibly take, which is B1, then I can say, well, then y of n must be less than or equal to B1 times the summation of the impulse response over all time. And that's finite, because capital B1's already finite. So the only way that the absolute value of y of n can be finite is if the summation is finite. And that's exactly the proposition from the previous slide. And again, the special case for FIR filters, as I said, on the slide, was that if I want to apply this proposition to an FIR filter, then the impulse response has finite extent. That extent is from 0 to some, say it's capital M coefficients. So my summation now is not from minus infinity to infinity, but I can reduce that to a summation from 0 to capital M minus 1. And I'm now basically taking a finite sum of finite values, which has to be finite. Okay. Okay, so there's the full story, right? Start with the convolution formula and work our way down to this answer. Right? And then finally, the final story that this summation has to be finite. Okay, but now from here on in, we're not going to really refer back to this. We're probably not going to refer back to very often, right? Because now we can now take this and make it more useful to us. Again, knowing that FIR filters are always bibostable, and that for IIR filters we have to make sure the poles stay inside the unit circle even after implementation, and we're bibostable. So bibostable. In theory, when we design the filter, make sure the poles are inside the unit circle. After we implement the filter, we still want to make sure the poles stay inside the unit circle. Okay, so let's put this in words. Again, these are two ways to interpret the condition that the absolute value of the impulse response has to sum to a finite value for the case of an infinite impulse response filter. So for a causal sequence, so these rules are two sides of the same coin. The second rule is more general. So the first rule is for a causal system, and the second rule is for either causal or anti-causal or two-sided even. For a causal, so rule number one, for a causal sequence, poles are inside the unit circle. And now that means that our system is, that if this causal sequence is the impulse response of an LTI system, then that LTI system is bibostable, provided the poles are inside the unit circle. For rule two, it's the unit circle has to be in the region of convergence. We've already talked about this. This is just a clear statement of that. And this is going to be true, again, for causal, anti-causal, and two-sided signals. In the class, we tend to not worry about the anti-causal case much. But anyway, the rule two is the more complete version. So the unit circle, if the unit circle is in the region of convergence of the transfer function, then we have bibostability. Here's an example, and we're going to apply both rules to the example. So it's what I had on what I asked you in the previous slide. So take a first order infinite impulse response filter and apply the rule. So here's our example. So it's a first order system, one pole location, poles at z equals a. The inverse Z transform gives us the impulse response a(n) step n. This has to hold for any value of a. I suppose, does it work for 0? Probably not so much. You say it should be not 0. All right, so interesting. Does it work for 0? Yeah, not so much. All right, so here's the example. So if we apply rule 1, we're saying the poles have, in this case there's only one pole location, but the pole location has to be inside the unit circle. This would tell us that from rule 1 that the pole location, which is at location z equals a, to make that inside the unit circle, the absolute value of a has to be less than 1. Again, the unit circle is a radius, a circle of radius 1. If we apply rule 2, then we look at the region of convergence and see if that includes the unit circle. And the region of convergence includes the unit circle only if the absolute value of a is less than 1. Get the same answer. Just that rule 2 is the more general case. Go ahead.
I was reading one of the textbooks, and one of the things it mentions is that you never have poles in the region of convergence.
Correct.
Why is that?
Well, you can see that because if I just for example, if I let z equals a, then what happens? One over 0. Yeah, and so we don't allow that to happen. So the pole locations are always, they form boundaries of what we could use for the region of convergence. So for every pole radius in our system, we have a different possible region of convergence. And for the causal, if we want a causal inverse, then what we really want is the region of convergence that lies outside all the poles. So therefore, we find the pole of maximum radius and say that the region of convergence is the area of the z plane outside of that circle equal to the pole of maximum radius. Or poles, because you could have more than two that have the same max radius. More or less okay. All right. I wanted to have a couple slides here on the connection between the Z transform and Laplace transform. Laplace transform is in the signals and systems class probably a little more common, and you've seen Laplace perhaps in the differential equations course here. So just to make the connection, they are connected, and they play a similar role in if you remember back to signals and systems class. So the Z and Laplace transforms for our use, one of the uses in signals and systems is to transform a difference or differential equation into algebraic equations that are easier to solve, right? We take the Laplace transform of both sides of the differential equation, and we work through the algebra to solve for the output Laplace transform, take the inverse Laplace transform to find the output in the time domain. And the same story in the case of difference equations, apply the Z transform to both sides of the difference equation, work the algebra to isolate the output Z transform, and then take the inverse Z transform of that to find the output in the discrete time domain. Now, it turns out they have a very similar effect on the signal that we're transforming. So first, they're both complex valued functions of a complex frequency variable. So in the Laplace domain and in the Z domain, a slice through that domain reveals frequency content. So in the Laplace case, the frequency content is on the imaginary axis. In the Z plane, so the frequency content is on the imaginary axis. For the Z plane, where is the frequency content? It's in the phase, but tell me angle. Yeah, it's in the phase, or angle. Okay, so here it is, right? So here's frequency, and it's basically along the unit circle. But more generally, the phase, it's in the phase of the Z variable. That's I think what you're trying to say. That's it. Okay, so it's in the phase of the Z variable. Exactly right. Just as in the Laplace case, the frequency content is in the imaginary component of the S variable. If we look at the operation that we perform in the Laplace transform or the Z transform, there's a transform kernel, and this is what we use to take the transform. So in the Z case, we sum over the signal in the time domain times the little h of n times z of minus n. So the z of minus n is the kernel. And that's the computational kernel that we use. The Laplace case is very similar. The kernel right, so we integrate against this complex exponential e to the minus st, and we integrate over all t, the product. Okay, but again, the kernel is here. Okay, so it looks like a completely different operation. They have nothing in common, but it's amazing. They do very much the same thing. So if we take the Cartesian, this Cartesian representation of the S variable, and we substitute it into the kernel for the Laplace transform, we get something that looks pretty interesting. So we put this in. We get, for S equals sigma plus j 2 pi f, place that right into the expression e to the minus st, and we can break this apart break the result apart at the minus sign. So we get two terms, e to the minus sigma t multiplied by e to the minus j 2 pi ft. It's a product. You go, okay, what's the big deal? Well, we're separating out this kernel into a dampening factor and an oscillation term. So this part right here is simply a complex sinusoid. The real part is oscillating, cosine of 2 pi ft, and the imaginary part's oscillating. Right, the sine of, well, minus the sine of 2 pi ft. This is a complex sinusoid. The Z plane, the Z transform does the same thing. I plug in again, now I'm going to plug in the polar representation of Z into the Z transform kernel, and the same thing happens, it turned out. So if I plug in r to the ej omega and I raise that to the minus n power, or minus nth power, I get the same two terms. I get a dampening factor and an oscillation term. That oscillation term is also a complex sinusoid. Its real part oscillates at cosine omega n, and the imaginary component oscillates at minus sine omega n. I use an Euler's formula. And then there's a dampening term. And that dampening factor depends on the value of sigma in the Laplace case and the value of r in the Z case. So if sigma is positive, what happens to the term? So if sigma is positive, does this one decay or not? It decays, right? And if sigma is 0, what happens? It's constant. And if sigma is negative, it grows without bound as time goes to infinity. Well, if we look at the dampening factor for the Z transform, if r is less than 1 in absolute value, sorry, other way around, if r is greater than 1 in absolute value, then what happens? Does it decay? Does it stay constant, or does it?
If r is greater than what?
If the absolute value of r is greater than, well, r is going to be a real number. So r is greater than 1. R is greater than 1, well, it's going to decay because of the minus n, right? The sign gives us, this minus sign is the opposite sense, right? So if r is 1, then what happens? Stays constant. And if r is less than 1 in absolute value, yeah, it will grow without bound as n goes to infinity. Okay, so this brings us, since there's a deep connection between Z and Laplace transforms, it turns out we can take designs of LTI systems in continuous time analog domain and map them to discrete time digital implementations. There are many ways to do that. And the reason there are many ways to do that is that there's no unique mapping from the Z to the Laplace domain or from Laplace to Z, because we're mapping one complex plane onto another. There are many ways to do that. There is one commonly used mapping. This has been around since the 1950s. It's called impulse invariance, and this was one of the very early ways to design a discrete time LTI system based on an existing continuous time LTI system. And the idea here in impulse invariance is to make the impulse response of a discrete time LTI system be a sampled version of the impulse response of the continuous time LTI system. Seems like a reasonable thing to do, but we know that whenever there's sampling, we have what? No matter how hard we always have aliasing. So no matter how careful we are, this method suffers from aliasing. All right, so let's give an example of this. And also, while we did the example, think about what the frequency selectivity is of the filter as we go. So here's the mapping for impulse invariance. It maps from the Laplace domain to the Z domain. So it means if I have a continuous time system, I know where the pole and zeros are. I simply pass it through this transformation to get where the pole and zero locations are in the Z domain. I have one free parameter. This is capital T, which is the sampling time. Once I choose the sampling time, I can then do the mapping numerically. So here I'm going to start out with a filter on the left in continuous time analog, or just continuous time. I have 2 poles and 2 zeros. This is a biquad in the S plane, so in continuous time. 2 poles, 2 zeros. And for bibostability, the poles have to be where in the Laplace domain? Left hand, I mean, lots of hints here, right? So the left-hand side, I've shaded it. So the left-hand side, the pole for a causal system, we need the poles in the left-hand side of the plane. Okay. Now, we also know that the frequency content in the Laplace world is on the imaginary axis. So it tells me kind of where the maximum, and this is in radians per second. If you look at the units here, 2 pi f, so it's radians per second. So it tells me that the maximum frequency of interest here is 1 radian per second. And I can convert that to hertz, which means I just have to divide by 2 pi. And so my sampling rate should be more than 2f max, which is greater than 1 over pi. So pick your favorite value of pi here. But we can, we know it has to be something greater than, a third or something. So we're going to pick the sampling rate to be 1 hertz to satisfy the sampling theorem. But we know we're going to have aliasing. And the reason we're going to have aliasing is that this imaginary axis goes all the way to infinity and down to minus infinity. So no matter what sampling rate we choose, we're going to get aliasing. It's a reality. If we apply the transformation letting fs equals 1, which is the same as letting t equals 1, then I get the following pole and zero locations in the S-plane, which I've plotted on the right here on a pole zero diagram in the Z-plane. And the nice thing is that this mapping preserves the notion of stability, right? So if you look at what happens, any part of the S-plane that's in the left-hand plane, that is to say the real part's negative, will map inside the unit circle. That's a good thing, right? So the region of bibostability for causal system in the Laplace case maps to the bibostability region for the Z case. The imaginary axis, which is simply where the frequency content resides, maps to the unit circle, right? So the mapping here, so if we look at what happens when s equals j 2 pi f, then this mapping is e j pi, j2 pi, f times capital T. That's the mapping, just oscillating. The right-hand plane, which is the bibo instability region, I suppose, for the pole locations anyway, maps to the region outside the unit circle. So now I've got to ask you, what is the frequency selectivity here? All pass is correct. So Appendix O in the reader. So again, also from the slide I had up earlier, 6-8. So we have pole and zero locations that are on the same angle, and the zero location in radius is 1 over the radius of the pole location. So for that configuration, we end up with an all-pass filter. It also tells you, just if you ever need to know it, the all-pass configuration for the continuous time case, for continuous time filters, the zeros are reflected about the imaginary axis from the pole locations. And that will give you an all-pass filter in continuous time. So all-pass it is. All right, let's talk about biquads in a little more detail. Remember, biquads are a building block, and we can use them in parallel and also in cascaded combination to realize a higher order transfer function. And I'll have a bit to say about that in just a second. So this will be, you'll need this next week in lab. So if I factor what I'll do is for a higher order system, say fourth order, then what I do is if I have a fourth order transfer function, then I can factor this so consider this to be fourth order. Then I can factor this into 2 second order systems. And in terms of implementation, I'd simply cascade these two second-order sections to realize this fourth-order transfer function. So I would need two biquads in cascade to realize this higher-order transfer function. And then the question is going to come up, okay, which order? Do I put H0 first and then H1, or do I put H1 first and then H0? It matters. It turns out it matters. In theory, it doesn't matter if I have exact precision calculation. It doesn't matter. But once I start using an implementation, saying, how do I implement the filter? So here I'm doing continuous time. So this is a continuous time slide. I have a Z transform up. So let me fix that to an S, which we will do very quickly. Okay. Now we're in the S plane. Very good. Sending will happen in the continuous time case. So again, if I want to implement a fourth order continuous time filter, it's just a cascade of two biquads in continuous time. The order matters, and so what you can do is try both and see which one is a better filter, better magnitude response, or whatever you're looking for. Simulation, so you can do this in SPICE if it's continuous time, or in discrete time case, we just run some test signals through and see what happens. So the discrete time case is easier. We can just simulate that on the computer, all possible combinations. As it gets more interesting, for a 10th order filter, there are a few more combinations. It's factorial, a lot of and then I also haven't told you how to choose the zeros yet, but we'll do that. So there's also another permutation in how you match the zeros with the poles. So you try all possible combinations of that. Simulation. So you're happy with one of the choices. But barring simulation, there's a nice rule of thumb using quality factors to decide what order to use. So again, we have let's start with a biquad, second order filter section, two poles and 0 to 2 non-trivial zeros. Suppose I should fix the slides on this one. So non-trivial zeros. So again, the transfer function is a ratio of two real-valued polynomials. Poles and zeros occur in conjugate symmetric pairs, or they're real-valued. The real-valued case does happen in practice. It's a little more common to see them as conjugate symmetric pairs. There's a notion of quality factor, which is a technology-independent measure of the sensitivity of pole locations to perturbations, which means that when I go to build this circuit out of resistors and capacitors, or whatever I'm using, the pole locations won't be exactly where I wanted them to be, because there's some tolerance in the resistor and capacitor values. There's some uncertainty in their values. That means there'll be some uncertainty in the pole locations. So for an analog biquad with poles at A plus and minus JB, again, where A has to be negative for bibo stability, you want the poles on the left-hand side of the plane, there's a very simple formula for the quality factor. And the quality factor is simply the absolute value of the pole location divided by, so here's the absolute value of the pole location, divided by minus 2 times the real component. The real component's negative, so minus 2 times little a is positive. We don't let a equal 0. That's forbidden here. That's an oscillator. It's a fine oscillator, not a filter. All right, so here is the quality factor, and a couple of interesting points. So for the smallest value of 1/2, this corresponds to a non-oscillating pole, real valued. As you let a go to 0, q goes to infinity. So when q is infinity, it's a metaphysical oscillator. It's the best oscillator you could ever imagine, which is great for oscillators, but bad for filters. So we'd love to have the Q factor in practice as low as we can get it. So again, here's some extreme cases. So if I have 2 real poles, it means that the imaginary component is 0, so B is 0. The quality factor is 1/2. This corresponds to an exponential decaying response without any oscillation. I got to be careful. A has to have no oscillation. A has to be. We'll do this on the next slide. This will give us an exponential decay response. when I have imaginary poles, again, in the limit as A goes to 0 and the limit Q goes to infinity, great for oscillation, bad for filters. All right, so let's look at the impulse response for a biquad with poles and no zeros, or to say I only have trivial zeros. So the impulse response with a biquad with poles A plus and minus JB, with, again, the rho component less than 0 for Biot stability, but no zeros, meaning no non-trivial zeros. If you do the inverse Laplace transform, you get a very familiar decaying sinusoid from all those differential equations you've solved in the past for linear constant coefficient case. Very familiar. So this is the impulse response of such a biquad, again, providing the initial conditions are 0. You look at the two extreme cases. When A is 0, this term goes to 1. And I have a beautiful oscillator when A is 0. When B is 0, the cosine term is just a constant. And so the response is just a decaying exponential because A is less than 0. So these are the two extreme cases. So I think about implementing this in implementing a simple single pole filter, and we can do a low pass filter here. So this is a really common interview question, and I've had it up before. So here's the input X, output Y. Type of filter and selectivity, it is low pass. It's a voltage divider, and so working voltage divider problems, very, very common on interviews, either on site or on campus. This one has an impulse response. It's in the reader. I want to make sure I get it right. There's some constant. Okay, so it's an exponential, decaying exponential. With a time constant RC. The pole location minus 1 over RC. Left-hand side of the plane for Biot stability. So consider a single pole at that location minus 1 over RC. With 1% tolerance on the RC values, the tolerance of the pole location is 2%. So first question, how many decimal digits correspond to 2% tolerance? So 2 mistakes out of 100. How many digits are you good to? Not 1 bit. How many decimal digits? So the error is 2 out of 100. Yes. How many digits are accurate? In other words, if I tell you the pole location is at 1.2345678, how many of those are really valid that I can really represent using RC? Where do I truncate around? 2 decimal, yeah, so 1.23 is about it. That's all I can guarantee. So I'm only good 2 parts out of 100, so I'm only good to 3 decimal digits, and that third digit isn't exactly right all the time. So that's all I get out of breadboard components. And how many bits correspond to 2% tolerance? So I have basically 1 bad bit out of 50, or one. If I think about out of every 50, I have the one mistake. So how many bits could I represent the pole location by? Basically, I want to pick the number of bits so that last bit has some error in it, but the other bits are good. 6. All right, so 6 bits gives me 64. So all this is 6 bits. So I get 3 decimal digits, and I get 6 bits. So what this leads us to is there's some unusual things, I guess. Suppose this is from talking to analog designers, which I'm not one. But for breadboard components, they tell me that the maximum quality factor they can really implement with passive components here is 25. Just RC network. For switch capacitor, which is a little bit more involved, it's an active circuit. Q can be a little bit higher. And then IC design, you can get a little higher than that. But it takes a lot of effort. What does that tell us? It tells us that when we go to look at a filter design, before we even build it, there are some limits on what quality factors we can tolerate. So if our initial design has got pole locations that give us crazy quality, high factors for the quality factor, we probably should redesign the filter. It's just not even worth trying out. We can simulate it all we want, but we're building it in a particular technology will probably not work very well. Okay, there's a similar idea for discrete time biquads, and the formula is a little more complicated, but this is what we'll need in lab for next week. And so I should say, so what does it tell us? So the quality factor tells us what order we should put the filters in, the biquads in, if we don't have the opportunity to simulate all possible cases. And for the analog case, it's not so different from the discrete time case. That we really want to put the biquads that are tending to oscillation last. So in terms of how we put the biquads in order, we want to go from low quality factors on the input side to high quality factors on the output side. So from left to right, from input to output, we want to put the biquads in ascending order of quality factors. And the idea is that if we put the stages that have decay in them early on, we clamp down the voltage range, which will cause us to have less oscillation later, because that oscillation happens at the end, not at the beginning. Okay, so for discrete time, it's a similar story. And I know this looks complicated, and there's an easier heuristic that we use in practice than this formula. Although we can also, I personally like this formula and use it for implementation. But for design, there's a simpler formula, which is at the bottom, to actually get a good design to start with. So for discrete time IR biquad, pole locations, again, conjugate symmetric. They could be real valued. If they're real valued, what's the quality factor? If I have 2 real valued poles, what's the quality factor? Better than 1. Yeah, it's the best we can do. So a real valued pole is the best we can do. It doesn't. The only time it would oscillate is if it's negative in real value. Then it's going to go. The impulse response will be plus minus plus minus plus minus. Okay, so there's a similar quality. So for poles that are conjugate symmetric, we can write. And here's the polar version of conjugate symmetric. If we let the radius r be the absolute value of the pole location, and that pole radius has to be less than 1 for bibostability. And we can use another intermediate variable, which is minus 2a, that also, if you remember, showed up in the previous definition. We can write out the quality factor for the discrete time case as follows. It's a little more complicated, but we end up with the same range of values. This is a formula in the end. The same range of values where 1/2 corresponds to decaying response and infinity corresponds to a perfect oscillator. So again, you can check some of the extreme cases. So again, for real valued poles, the imaginary component 0. And if you kind of work through the algebra on this one, you end up with a quality of factor of 1/2. It's a repeated root, and so this is the impulse response for that, but it's decaying exponential terms. A is real valued. Poles on a unit circle, r is 1, so you let in the limit as r goes to 1, the denominator goes to 0, and the Q factor goes to infinity. Again, great for oscillators, terrible for filters. So again, this is also an ad hoc. Well, this one's just a simpler formula for the case of imaginary poles. Just from experience, if we're using 16-bit fixed point processor with the 40-bit accumulator in conventional DSPs, then the max Q we can support is about 40. So if we come up with an initial design and the Q is too high, we should do another design method. We're wasting our time to implement on the 16-bit DSP. Floating point is going to have a much higher Q tolerance. So if I do a 32-bit float, I don't remember the number of that offhand, I would probably intuit that it's 60 or something for a 32-bit float. It's pretty high. Because you have 24 bits of mantissa plus sign. Okay, so what do we do on the design side? On the design side, you can either embed this as part of the design formula, or more simply, you can simply constrain the radius of the poles to be away from the unit circle. So you can say, where do we get in trouble? We get in trouble when the poles get close to the unit circle or too close. So in the filter design, we can say, limit the filter pole locations to be no greater than, say, 0.92. And I'll have demos of this on Friday. And that's built into MATLAB, it's built into LabVIEW, it's built into a lot of... So you can control the pole configuration and at least the radii of the pole locations, so that you have a better implementation from that design. Okay, so I guess I'll see you on Friday. And homework's due on Friday.
We'll be in ENS.
We'll be in ENS on Friday.
You say we'll be in the end, that's not bad.
Yeah, it'll be the last time that we'll be in ENS for this semester.